This is Kruti Jaipancholi, Assistant Professor in LJ Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject fiber optic communication. So friends, till now you learn about the various waveguiding structure, the structure of a fiber optic cable. So that everything you learn. Now we will focus on the other part of the optical fiber. So from this video you will learn about the signal degradation in optical fiber. So friends, you have also learned about the various fabrication technique. So now we know about it, that how the fiber fabrication, how the selection of the material that causes the attenuation less transmission or there is a degradation in the signal. So the question in this particular video, you will learn about the attenuation, causes of the attenuation units and the various examples. So friends, the signal attenuation and distortions in the optical fiber. The question is, what are the loss or the signal attenuation mechanism in the fiber? The another question is, why and to what degree do optical signals get distorted as they propagate down a fiber? So these are the questions that comes into our mind. So signal attenuation, many a time referred to as a fiber loss in optical fiber, largely determines the maximum repeater-less separation between the optical fiber transmitter and the optical receiver. So it's an important property of the optical fiber is signal attenuation, degradation. So it is also known as the fiber loss or the signal loss. The signal attenuation of the fiber that determines the maximum distance between the transmitter and the receiver. So attenuation that also determines the number of repeaters required. Maintaining the repeater is a costly affair. So you want to go for the distortion less transmission. So for the distortion less transmission, we need to repeat the signal. Okay, so for repeating, for maintaining the signal as the original one, we have to put the repeater. So this attenuation, if it is a very large, there is a large number of the repeaters we want in our system. So this way the signal attenuation and the distortion study, that is also important. Another important property of the fiber, that is the distortion mechanism. As the signal pulse travels along the fiber length, it becomes the more broader. Okay, so after the sufficient length, the broad pulses that starts the overlapping with the adjacent pulses. So this is what the pulse broadening of the fiber. So whenever initially there is no overlapping between the two pulses, but after the some distance it starts the overlapping, and this creates the error in the receiver. Hence, the distortion that limits the information carrying the capacity of the fiber also. So, signal distortion that cause the optical pulses to broaden. One line answer of this, that is what is the signal of attenuation, or how the distance you can see. You can say that whatever the input pulse, if you will get that pulse at the output end, that broadening of the pulse that signifies the distortions in the transmission. So the overlapping the pulse, the creating errors in the receiver output, and that resulting in the limitation of the information carrying capacity of the fiber. So now very first we will focus on to the attenuation. So what is the attenuation? So attenuation is the measure of the decay of the signal strength or loss of the light power that occurs a light pulses propagate through the length of the fiber. What are the causes of the attenuation? So, normally 90% of the attenuation that is caused by the Rayleigh scattering. While the fiber that get band, some the loss due to this microbanding that can be also present. So, microbanding of the optical fiber that also contribute to the attenuation of the signal. So, the rate at which the light is absorbed is dependent onto the wavelength of the light and the characteristics of the particular glass. Glass is the silicon compound. So by adding the various the additional chemicals, okay, what we can be? We can do the we can change the properties of the glass. Okay, so by adding such kind of the impurities, again the property of the glass that can be changed. The Rayleigh scattering that is a wavelength dependent and reduces rapidly as the wavelength of the incident radiation increases. Okay, so this is about the causes of the attenuation. So attenuation of the fiber that is governed by the materials from which it is fabricated, the manufacturing process and the refractive index profile chosen. This attenuation that is measured in the dB per kilometer. Now the next is about the attenuation unit. So attenuation that leads to the loss of the power along with the fiber and the output power that is less than the coupled power. So let the coupled optical power, that is suppose the P0 at the origin the value of the Z that is equal to 0. So the power at the distance Z that is given by the Pz is equal to P0 e raised to minus alpha P into Z, where alpha P that is the fiber attenuation constant per kilometer. It gives us the value per kilometer. So alpha P is equal to 1 upon Z ln P0 upon Pz. So alpha dV per kilometer, in the log we can write it is the 10 1 upon Z log P0 upon Pz. So attenuation that is also the function of the wavelength. As we have also studied in the chapter number 1, the attenuation, okay, that is the first window, second window, third window and which particular window that we need to use for the transmission. Okay, so you know that according to the wavelength, the attenuation that may appear and wherever the attenuation is less, that window can be selected for the transmission. So the alpha dB per kilometer, it is 4.343 alpha P per kilometer, and the parameter is known as the fiber loss or the fiber attenuation. So now we will solve the example based on this. The example number 1 is a low loss fiber has an average loss of 3 dB per kilometer at 900 nanometer. Compute the length over which power decreases by 50% and power decreases by the 25%. So now the alpha is equal to 3 dB per kilometer. The power decreases by 50%. P0 by Pz is equal to 50%. Okay, and the value that is the 0.5. So it is given by alpha dB per kilometer. It is, we have studied the equation that 10 1 by Z log 0.5. So now the alpha is equal to the 10 log 10 1 by z log 0.5. But what is the value of the alpha? 3 dB per kilometer. So we'll put the value inside the equation. That is 3 is equal to 10 1 by z log 0.5. So z is equal to 1 kilometer. Now the another example. Alpha is equal to 3 dB per kilometer. Power decreases by 25%. Okay. So P0 by Pz is equal to 75%. Okay. So 25%. So it is the 0.25. So now it is given by the alpha dB per kilometer is equal to 10 1 by z log 0.25. So now we'll put that value in the alpha equation. So alpha is equal to 10 1 by z log 0.25. But what is the value of the alpha? Alpha is 3 dB per kilometer. So it is 3 is equal to 10 1 by z log 0.25. So answer is z is equal to 2 kilometer. Example number 2. That is for a 30 kilometer long fiber attenuation, 0.8 dB per kilometer at 1300 nanometer. If a 200 microwatt power is launched into the fiber, what is the output power? We need to calculate over here. So value is given, alpha is equal to 0.8 dB per kilometer, z is equal to 30 kilometer, P0 value that is 200 microwatt. So if you will convert that microwatt into the dBm, it is the 7 dBm. How to calculate? Okay. So formula for the conversion of the milliwatt to dBm. Okay. You have to convert this 200 microwatt into milliwatt. Okay. And put that milliwatt value in this equation and finding out the answer, that is the 7 dBm. Okay. So now the attenuation in the optical fiber, it is given by the alpha is equal to 10 1 by z log P0 upon Pz. So now put the value of the alpha and the z in the equation. P0 value we are putting over here. So our answer is the 200 microwatt divided by the Pz is equal to 10 raised to 24. Okay. So it is the Pz value is the 0.7962 microwatt. So this is about the examples related to this attenuation. So thank you very much everyone.